This is the first part of the video for section 6.1. In this one we're going to talk about the inverse circular functions. We've actually already talked about these somewhat, but now we're going to look at these as actual functions. So first let's just talk about inverse functions. If we've got a function f, then every element in the domain corresponds to only one element in the range. In other words, if the point AB lies on the graph, then there's no other point on the graph that has A as a first coordinate. Another way you can say this is that for it to be a function, you can't repeat x values. Now, we can have repeated y values, so we can have other points that have B as a second coordinate, because the definition of a function allows the range elements to be used more than once. So the range elements, the y's can be repeated, the domain elements, or the x's, can't be repeated. Now what we're going to talk about here is a little bit different type of function. If we have a function defined so that each element in the range only gets used once, then it's called a one-to-one function. This one would have each element of the domain, so each x only gets to be used once, and each y only gets to be used once. So nothing gets repeated. So we don't repeat any x values. That's for it to be a function. For it to be one-to-one, then we also can't repeat any y values. Now, one way to tell if something is a one-to-one function is to do the horizontal line test. If a horizontal line intersects the graph more than once, then it's not one-to-one. And then finally, to define an inverse function, for one thing, we write it sometimes as f with a little -1 up here. This is not a negative exponent. This just symbolizes an inverse. This is the set of all points yx, where the point xy was on the original function. In other words, all we're doing with inverse functions is we're taking the x's and y's and switching them. The last thing about these is that we don't want to confuse this -1 right here with a negative exponent. This doesn't mean that we're taking 1 over f of x. It just represents the inverse function of x. For our summary of inverse functions, in a one-to-one function, each x value corresponds to only one y value, and each y value corresponds to only one x value. If the function f is one-to-one, then it has an inverse function, and the notation for this is f with the little -1. Now when we switch the x's and y's, we also switch the domains and the ranges. So the domain of f is the range of f inverse, and the range of f is the domain of f inverse. Another way to think about this is that we're switching the coordinates. So if the point AB is on the graph of f, then the point BA is on the graph of f inverse. When we look at the graphs of these, the graphs of a function and its inverse are reflections of each other across the line y equals x. And that's because we switch the x's and the y's, and it makes it reflect across that line. Well, let's look at some specific inverse functions that have to do with our trig functions. The first one we're going to talk about is the inverse sine function. There's another notation for this. One way we can write this is sine with the -1. You've seen this on your calculator. Another way to signify this function is we call it arc sine. So arc sine means actually the inverse sine. And all this means is that we're putting the value in here and it's giving us back the actual angle. So the y here is the angle in the interval from -π/2 to π/2 that has a sine value of x. Now let's look at our graph of our sine function. Here's part of the graph for our sine function. Now the problem with this one, if we're trying to find the inverse function, is that if you look at this, this is not one-to-one, because it would fail a horizontal line test. We've got lots of places where if we drew a horizontal line, it would actually intersect the graph an infinite number of times, not just twice, but a whole lot more than that. What we're going to do is cut down this domain. We're going to restrict the domain so that we don't get any repeated y values. We're going to make it go just from negative pi over 2 to pi over 2. So we're just going to take this much of the picture. We're going to erase the rest of our sine function. So we're going to erase it on this side and on this side. That's why up here it says it's the number in the interval between negative pi over 2 and pi over 2 that has a sine of x. This is the sine of x function. The domain for sine of x, it would be normally negative infinity to infinity, but we're going to restrict it so that it's only going from negative pi over 2 to pi over 2. And then for our sine of x function, our range is negative 1 to positive 1. Remember on our graphs we had the minimum value was negative 1 and the maximum value was positive. Now if we're thinking about the domain and range of our inverse function, we're just going to take these two and switch them. So the domain is negative 1 to 1, because that was the range for our sine function. The range is going to be our restricted domain that we decided on for the sine function. So that's going to be negative pi over 2 to pi over 2. That means when you come up with an answer for an inverse sine, it has to be a number between these two values. If you're doing radians, it's between negative pi over 2 and pi over 2. If you're doing degrees, it's between negative 90 and positive 90 degrees. That also, if you think about what quadrant that's in, that puts this in either quadrant 4 or quadrant 1. But if it's in quadrant 4, it's going to be listed as a negative angle instead of a positive angle that's between 270 and 360 degrees. This is going to be given as just a negative angle. So let's find some function values for the inverse sine. Here, if we're trying to find the arc sine of 1/2, that's the same as the inverse sine of 1/2. So in other words, this is the value for the sine of an angle. We want to go back and find out what the angle is. So one way we can do this is we can just take these two things and switch them and use the inverse of this function, which would just be the sine function. So we can say 1/2 is the sine of y. So I'm switching from this function to the inverse, and then I'm just making these two things switch places. And then what we want to do is figure out an angle that has a sine value of 1/2. This would be one of our special angles. It would be pi over 6 or 30 degrees. We can do the same thing with this. We can use the inverse of this, which would just be the sine function, and then we're going to have these two things switch places. So the negative 1 comes over here, and the y comes over here and goes inside of our sine function. So now we're looking for an angle that has a sine value of negative 1, where sine is negative 1, is at 270 degrees or 3 pi over 2, but what we want for this is a negative angle. So we're going to, instead of 270 degrees, we would say it would be negative 90 degrees or negative pi over 2. We're going to do the same thing with this. We're going to go from the inverse sine to the sine, and then we're going to have these two things switch places. Now we're looking for an angle that has a sine value of negative 2, except this is not possible. The value of sine has to be between negative 1 and positive 1. If you go back and look at this just in terms of the inverse sine function, the domain for inverse sine is only between negative 1 and 1. Negative 2 is outside of that interval. So this value is not in the domain of the inverse sine function. Now, I want to show you one other way to do these. I was doing all of these by just switching to the inverse function and then switching the values. I'm going to show you another way just in case you didn't quite get this one. And that is, we can always think of sine and inverse sine being inverses of each other. On this one, for example, if we want to cancel out the inverse sine, we could use its inverse function on each side. Its inverse function would be sine. So we could take the sine on both sides. That would give us the sine of y on this side, and over here we'd have sine of inverse sine of negative 1. The sine and the inverse sine are going to cancel each other out. So then we end up with sine of y equals -1. So we end up at the same place we did here, it's just going about it a little bit different way. We can do the same thing with this one if we remember that sine and arcsine are inverses of each other. So we could take the sine of both sides here. On this side we'd have the sine of y. On this side we'd have the sine of the arcsine of 1/2. These two are inverses, so they cancel each other out. And we just get the 1/2 there. Now, since we're thinking about the inverse sine function as a function in its own right, we're going to look at what the graph would look like. So if we think about values for inverse sine, remember we're plugging in the values, what we're getting back out are the angles. So all of these values, if we're looking at the graph, all of these values have to be in radians. If we're talking about the graph of this function, we can't talk about degrees. So if you're trying to graph this, make sure that you've got your calculator in radian mode. So these are some values for inverse sine. And if we look at these values as x is going from -1 to 0, our y values are going from -π/2 up to 0. So on that interval, the inverse sine increases from -π/2 up to 0. And then if our x goes from 0 up to 1, then our y values are increasing again from 0 up to π/2. That means that this function is increasing on its whole domain. If we look at the picture of the actual graph, we've got 3 main points that we can look at. These are the two ends of our domain at -π/2 and π/2, and then we've got this point in the middle. And this is what it would look like on your calculator if you're using the Zoom Trig window. So all the facts that we know about inverse sine, we know that domain is -1 to 1. The range is -π/2 to π/2. The graph is increasing and continuous on its entire domain. That means there aren't any gaps or jumps or vertical asymptotes. The x-intercept is right here, so it's 0, and that's also the y-intercept. So those are both 0. And then this graph is symmetric with respect to the origin, which makes this an odd function. That means that if we've got the inverse sine of -x, we can pull that negative to the outside.